Hello, and welcome to the second week of Math 4400. So today the topic is the Euclidean algorithm. Okay, and get straight to it. So the Euclidean algorithm is going to be a tool that comes up when we try and justify the unique factorization theorem. So remember, the unique factorization theorem just encapsulates this basic fact about integers or natural numbers. I have it state here for natural numbers. So if you have a natural number, then there's exactly one way to write it as n is equal to a product of prime numbers. So each prime sort of appears at most once, and you have it to some power, some positive power. And so to make this unique, I've just written that we order the primes p1, p2, p3 in increasing order. So like 6 is 2 times 3 would be sort of the factorization we write down instead of 6 is equal to 3 times 2. And that's just because otherwise you have to say unique up to reordering. Okay, but this is a fundamental property of the natural numbers and the integers that you have these factorizations into primes. And it's useful both in applications and in theory. So it's something we really want to understand. And again, it's one of these facts that is built into our brains. Like we learn it so early in our education. It's hard to see that this is even something that needs justification, but it actually is. Okay, so there are two parts really to this statement. One part is existence. So that's saying that if I take a natural number, that there is some way to factorize it into prime numbers. So for example, if I take 6, I can write it as 3 times 2 or 2 times 3, good. So I can factorize 6 into prime numbers. And then uniqueness is the second part of this result, which says not only can I factor it into prime numbers, but really there's just one way to do it. So that's this exactly one way, the statement of the theorem. And well, it turns out existence is a little bit easier to justify. And uniqueness will need to introduce another tool, and that tool for uniqueness will be the Euclidean algorithm. And somehow, well, existence is something that's going to hold, this kind of factorization will hold more generally. So in some other related situations we'll talk about later on in the class, but uniqueness is something a little bit more special. That's special about the integers as opposed to other different number systems we'll talk about later. Okay, but so let's, so today I'm going to give the justification for existence because it's pretty easy and introduces an important idea. And then afterwards, we'll discuss the Euclidean algorithm and related topics. And this is a tool for proving uniqueness, and we'll actually come back and explain why this uniqueness holds using that on Thursday, or for the Thursday lecture. Okay, so existence. So the idea for why prime factorizations exist is just, if I take a number and it's not prime, okay, so if I take a number and it's prime, then if you have a prime number, like that is its prime factorization, so you're set. And if it's not prime, well, by definition, that means it has like a proper divisor. So that means you can write n as a product of a times b, where a and b are two positive integers greater than 1. So if you think back, like the definition of prime is that the only divisors are the number in itself. And so if you're not prime, then there is such a factorization to a and b. Well, these a and b may not be prime themselves, but if a is not prime, well, you just repeat. So you say, well, if a is not prime, then a is equal to c times d for cd greater than 1, and so on. And you do the same thing for b if b is not prime, and then so b. So then, yeah, so if b is a is equal to cd, then n is sort of equals c times d times b, and then you just treat each of these individually. And somehow, because these are always proper divisors, you're always making these numbers smaller. And if you keep on going forever, and like if you keep on going as long as you can, eventually that's going to stop, because like if you start with 1,000,000, you can only make these numbers smaller at most 1,000,000 times, but eventually that's going to stop. So this is sort of the idea for why prime factorizations have to exist, just because you can try and construct them this way. This is also, somehow this describes how you would naively like the most naive algorithm for trying to factorize a number is you just start trying to divide it by things. If you can't divide it by anything smaller, then it is a prime number. And otherwise, like you get one factor and then you just repeat. Okay. So this is the idea. You can turn that into a proof, but there's maybe a little bit nicer way to write down a proof cleanly. And I wanted to go through that because it uses an important property of the natural numbers. The natural numbers is synonymous with the positive integers, and here I've written this saying positive integers. Okay, so this is the well-ordered axiom. And this just says that every non-empty subset of positive integers has a smallest element. So this is a pretty intuitive fact. If I give you a bunch of numbers, there's a smallest one, like as long as they're all positive. Some of the main thing is in establishing that is they give you sort of okay, and it's an axiom. So an axiom means something we're going to just accept as true. But if you try and think of how to justify that in your head, like the idea is just even if you have like an infinite set of numbers, an infinite set of positive numbers, if you fix one of them and then look at everything, like definitely the smallest element will be less than that. And then once you look at less than that, then you only have finitely many things. And so you do the same kind of thing. You just sort of throw out things until you get to the smallest one. Okay, and because somehow you've reduced to finiteness at some step, then you're okay. But okay, so this well-ordered axiom is what kind of encodes this idea that I can keep going just by replacing these things with smaller numbers if they're not prime, and that eventually that will stop. I want to go ahead and write down a proof cleanly because it's sort of fun and you get to see a nice proof technique. Okay, so let's say, suppose there's an integer n that does not admit a prime, that does not factor into primes. So it does not factor as a product of prime numbers. So this is step one. So we're going to show that prime factorizations exist. So this is supposed to be even a positive integer. It's just because of the statement I gave. So we're going to argue by contradiction. So one way you can establish a logical fact is you can assume the opposite holds and then obtain a contradiction with something you already know is true. So here we're sort of arguing by contradiction. Okay. Okay. So this is how we're starting. We're supposing that such a number exists. And so what's the next step? Well, I'm going to apply the well-ordered axiom. I'm going to apply it cleverly to the following set. So I'm going to let S be the set of positive integers not admitting prime factorizations. So not writable as a product of prime numbers. Okay. Then S is non-empty. By our assumption. So this is some of the key step. To apply the well-ordered axiom, it's not just any subset of natural numbers, of positive integers, it's a non-empty subset. So that's where we're going to use our assumption. We assume that there is some integer prime factorization. And so that means the set of all such integers is non-empty. So, okay, so let me say that here. So by well-ordered axiom, there's a smallest number, there's a smallest element, n in S. Okay. Well, n is in S, so it's not a product of prime numbers. N is not a product of prime numbers. So in particular, it's not prime. So I can factor n as a times b for a, b positive numbers. Not just positive, greater than 1. I mean, I guess really everywhere I should be saying integer n greater than 1. So let me change that. Just because 1 is not a product of prime numbers because 1 is not a prime number. So sorry, I should have said integers greater than 1 everywhere. Okay. I'm not going to re-record this because, well, it's good for you to observe my humanity and to see that even after 15 years of studying mathematics, I still make mistakes, but also because I don't want to start the recording over. Okay, good. So right, but I have n is the smallest number that doesn't admit of prime factorization. So I'm assuming there's some number that doesn't exist of prime factorization. And then well-ordered axiom gives me that there's a smallest such. Good, that smallest such, it's not a product of primes. So in particular, it's not a prime. So I can write it, so it has some factorization to smaller numbers a and b. They're both still greater than 1. Well, since a and b are smaller than n, that means a and b are not in S. Because n is the smallest element of S. But in S is a set of things that don't have prime factorizations. So a and b have prime factorizations. But then so does their product. Because I can sort of just take all the prime numbers that multiply together to give a, and then take all the prime numbers that multiply together to give b, and just smash them together. And that gives me a factorization of n. But this is a contradiction. So that little lightning bolt means contradiction. And this is how proof by contradiction works. Like, you sort of, if I get a contradiction, that means the thing I started by assuming wasn't true. So that means sort of there was no way, and somehow it means there was no way to take an integer, to find an integer that does not factor as a product of prime numbers. Good, so that's one way that you can make this proof idea that there exists, that every number has a factorization to prime numbers. That's one way you can turn this to a rigorous proof. There are other ways you can write this down as well. Good, but again, this is just existence. All we said in that proof was that you can find factorizations into prime numbers. We haven't said anything about uniqueness yet. Okay. And so to talk about uniqueness, well, we're going to need to make a digression. We're going to have to introduce another idea before we can set up our tools. And that's leading us to the Euclidean algorithm. But let me make just an elementary definition to start out with. If we have two integers, a and b, so we can write that as a and b are contained in z, then we say that b divides a, or equivalently, b is a divisor of a, or if we write this in symbols, just b vertical line a. So this vertical line is the divides symbol. So these are all equivalent statements, or these are all ways to say the same thing. So we say that, well, if b divides a, which literally means if there is some other integer such that a is q times b. Okay, so again, and this is exactly what it's always meant for b to be a divisor of a, like it's what it's meant since elementary school. But this is just to make it precise and write down some notation. This b divides a symbol is very useful. Okay, so for example, 3 divides 12, because 12 is 4 times 3. Okay, 5 does not divide 12. No surprises there. I mean, somehow I don't even really know how to say this except to say 5 does not divide 12. I say I don't know how to say this. The next line will explain how you can sort of say this, that 5 does not divide 12 a little bit more precisely. So if you remember way back to elementary school, when you first learned division, when you did long division, you didn't just stop, like if 5 didn't divide 12 evenly, you didn't just stop there. You computed what the remainder was. And that turns out to actually be very useful for us right now and continuing throughout the rest of the class. So we want to formalize that notion, the notion of division with remainder. And so we just do the setup like above. We have positive integers, we have integers a and b. We're going to divide by b, so we want b to be non-zero. And then so you can rephrase division with remainder by saying there are unique integers q and r such that a is equal to q times b plus r, and 0 is between r and the absolute value of b. So this is exactly what it means to divide with remainder. So if you remember, so doing long division, at least when I was in school, we wrote it like this. I don't actually know if you guys still write it like that, but well, way back in my time, we did. And so Q is what was called in elementary school the quotient, and R is the remainder. So A, so you try and get as close as you can to A with a multiple of B. So Q is the multiple, and B is sort of the thing you're trying to take and divide A by. And then, well, you can only get so close. And then you're left with this R, which is the remainder. Okay, and so going back to this example, so 5 did not divide 12, but the remainder was 2. And 4 divided 3, or sorry, 3 divided 12, and the remainder was 0. So somehow B divides A if and only if this remainder, when you write it like this, is 0. Okay. Again, that's not news to anyone who learned long division in elementary school. It's just writing it down as a useful formula. So writing this A is equal to QB plus R. So, right, so let's do this in a couple of things just to make sure we're all on the same page. So, okay, if A is 12 and B is 3, so I'm just trying to compute the, I'm trying to divide 12 by 3. Well, we already wrote that above. We got 12 is equal to 4 times 3 plus 0. So this is B, this is A, this is Q, and this is R. Okay, if A is equal to 12 and B equals 5, well, 12 is 2 times 5 plus 2. So the closest we can get to 12 when we're trying to, if we try to divide by 5, is 10. Like the closest multiple of 5 to 12 is 10. So okay, so we get to 2 times 5 plus 2. I guess when I say closest multiple, I should say closest multiple it's sort of less than 12. In this case, it's true, but in general, you're always looking, when you're doing this division, you're looking at the closest multiple that's less than the number you're trying to get. So yes, in this case, A is 12, Q is 2, B is 5, and R is also 2. So the remainder is 2. Okay, and then I wrote one where I'd actually have to do a long division. You might be able to do it in your head, but I'm pretty bad when I try to do this kind of thing in my head. So I'm trying to divide 107 by 6. Okay, and so first I put a 1 up here and I get a 6 below my 10. I sort of subtract that off, and so I get sort of 47. Okay, and then I guess I should do 7 times 6 is 42. I'm left with just 5, and I'm in the last spot, and 5 is less than 6, so I can't do anything else, so the remainder is 5. So, okay, if I rewrite this out, then I get 107 is 17 times 6 plus 5. So again, A was 107, B was 6. So I was dividing 107 by 6. Q ended up being 17. That was sort of the closest. 17 times 6 was the closest I could get without passing 107 using a multiple of 6. And then the remainder was 5. Okay, so that's the recap of long division. I know that's riveting stuff, but somehow long division is more powerful than we realized. Okay, so we're going to use that in a second, and we're going to use it to compute greatest common divisors. So if A and B are two integers, they're not both 0, then we write GCD of A and B, or greatest common divisor of A and B, for the largest positive integer m, such that m divides A and m divides B. So if I just have some positive integer dividing both of them, I call that a divisor. And if I take the largest divisor, so the largest, yeah. So if I have so m divides A, that means m is the divisor of A. M divides B means m is the divisor of B. So if m divides A and m divides B, m is a common divisor of A and B. And then if I take the largest sum m, that's the greatest common divisor. Okay, so for example, the greatest common divisor of 21 and 14 is equal to 7. These are both multiples of 7, but 21 is 7 times 3, 14 is 7 times 2. So, well, you can convince yourself there's no larger divisor. Actually, sort of, when I just said that out loud, what was I doing? Well, I said 21 is 7 times 2, and 21 is 7 times 3, and 14 is 7 times 2. What I was doing is I said out loud the prime factorizations, and then again, from elementary school, you know how to compute the greatest common divisor once you know the prime factorizations. You just took the overlap. So here we had 7 times 3 is equal to 21, 14 is 7 times 2, and then sort of the overlap of the factorizations, the prime factorizations, is just 7. Okay, so that's one way we computed GCDs back in elementary school. And this does work. Like, this is a way you can compute GCDs. I want to give you 2 warnings about this method. The first is that, well, of course, it's easy to do for 21 and 14. If I gave you some pretty big numbers, then you'd have to factor the numbers first to do it this way. Excuse me. Well, and we've already talked about this a little bit, but let me just reiterate, it's hard to factorize numbers. Like, it's hard to factor numbers in general. It's hard to find prime factorizations of big numbers. And so, well, okay, maybe this is just a hard problem, but we'll see in a second it isn't. So we'll see in a second there's a much quicker way to do it that doesn't involve finding the prime factorizations. Okay, so that's the computational warning. The other theoretical warning is just, and I want to point out, we're working towards showing this uniqueness statement for prime factorizations. And somehow, like, this algorithm for computing the greatest common divisor, this prime factorization method of computing the greatest common divisor, the reason it works is because prime factorizations are unique. So that's sort of a good thought exercise to think about why you need uniqueness of prime factorizations for this method to work. But so somehow, like, at least for what we're doing right now, we're about to use GCDs to help us prove that prime factorizations are unique. So we definitely don't want to sort of be thinking of them as something you get from uniqueness of prime factorization. Okay, so that's sort of a theoretical warning I wanted to make. So if we don't want to compute them that way, how will we compute them? Well, we're going to use the Euclidean algorithm. So what is that? So say I want to compute the GCD of 2 numbers, A and B, 2 integers A and B. So, well, what am I going to do? Step 1 is I'm going to write A is equal to QB plus R. So I'm going to sort of apply long division to express A in terms of some multiple of B and the remainder. And then the key observation here is that the GCD of A and B is actually the same as the GCD of B and R. So I'll explain that in a second, but the reason that's helpful is because like this B and R, like this is, R is smaller than A. So R is in fact, okay. So if I assumed A is greater than B anyway, then R is smaller than A. So this gives you a way to sort of take the GCD of two big numbers and replace it with the GCD of two numbers where one of them is smaller. Excuse me. And we're going to iterate, the Euclidean algorithm basically just iterates this until you get just the GCD of two very small numbers. And so you just have to do a bunch of divisions on the way. We'll see that in a second, but let me justify this observation that if A is equal to QB plus R, then A and B have the same GCD as B and R. So what do we need to check? So we need to check two things. So we need to check if D divides B and D divides R, then D divides A. And then two, if D divides A and D divides B, then D also divides R. Okay. So it's just saying, so if you have some divisor that's a common divisor, this first sentence says if you have a common divisor of B and R, then it also divides A, but it already divided B, so it's a common divisor of A and B. The second one says if you have a common divisor of A and B, well, it also divides R, so then since it already divided B, it's a common divisor of B and R. Okay, so if you can go both ways, then these numbers really have to be equal. And really what we're checking is we're checking all common divisors. Like a common divisor of A and B is also a common divisor of B and R. So in particular, the greatest common divisor, sorry, let me rephrase that. We're checking the common divisors of A and B are the common divisors of B and R. So the greatest one is also the same. Okay, but here we have A is equal to QB plus R for the first one. Well, so this is equal to Q times, well, D divides B, so I can write B as sort of D times C. Then R divides, D divides R, so R is D times E. And I just factor out the D, so this is D times QC plus E. Okay, so good. I just use this fact that I can express A in terms of B and R, and then the fact that D divides B and D divides R, and then I just pull out that D and I see that D divides A. Conversely, I can do the same thing over here in the second one. So if D divides A and D divides B, I want to see it divides R. So I can do the same thing. I just have to first rewrite A equals QB plus R as R is equal to QB minus A. Okay, and then I'll just factor out sort of the D from B and factor out a D from A, and I'll find that D divides R. Okay. So basic observation, but essential to what comes next. So this Euclidean algorithm for computing GCDs is that when I do this long division, so A is equal to QB plus R, the GCD of A and B is the same as the GCD of B and R, and that lets you sort of move to sort of taking the GCD of some smaller things. So let me just, before I say what the Euclidean algorithm is in general, let me just do it to compute the GCD of 60 and 22. Here I've written down the prime factorizations. So using the prime factorizations, of course, we can check that the GCD is 2, but we're going to do it a different way without saying anything about prime factorizations. Okay, so good. So we have 60 is equal to 2 times 22. That gives me 44, so plus 16. So this is my A is equal to QB plus R. And so by the above, the GCD of 60 and 22 is the same as the GCD of 22 and 16. Okay, and then I'm just going to now do the same thing but with 22 and 16. So I divide 22 by 16. Well, I just get 1 times 16 plus 6. So this is then equal to GCD of, so again, so I'm just applying the same statement, but now to this expression. And that gets that the GCD of 22 and 16 is equal to GCD of 16 and 6. But this is still equal to the GCD I wanted to start with. I was trying to compute to start with, so good. But now I do the same thing. Whoops. Sorry, I scrolled. I didn't need to. But so I do the same thing now with 16 and 6. So 16 is equal to 2 times 6 plus 4. So this is equal to GCD of 6 and 4. And 6 is equal to 1 times 4 plus 2. So this is equal to GCD of 4 and 2. Okay, well, this is getting a little ridiculous, but still I'm going to go all the way. And then I get 4 is equal to 2 times 2 plus 0. So this is equal to GCD of 4 and 0. And well, once you get down to one of the entries is 0, then the GCD is always just the other entry. So every number divides 0 because you can always write sort of 0 as 0 times, like 10 divides 0 because 0 is equal to 0 times 10. So when you take the GCD of a number and 0, you just get that number back. So that gives us 4. Good. So by just applying this observation and just doing repeated divisions, we got down from the GCD of 60 and 22 to just 4. And all we had to do was divide. Okay, and so that's what you do for the Euclidean algorithm. So you start, if you're computing, GCD of A and B, well, first you divide A by B, and so you get A is equal to Q1B plus R1. So you get GCD here. So the GCD of A and B is equal to the GCD of B and R1. Okay, so then now you divide R1, you divide B by R1. So we get B is equal to Q2 R1 plus R2. And again, same, applying that key observations over and over, we get that the GCD of B and R1, GCD of B and R1 is the same as the GCD of R1 and R2. And we get, well, we do it again. We divide R1 by R2. We call the quotient Q3, and the remainder R3. And this is the same as the GCD of R2 and R3. And so on. And we're left just with here, the GCD. Okay, we have to do this m times, let's say. And then we're left with the GCD of Rm minus 1, 0, which is just Rm minus 1. So if you keep on doing this over and over, eventually you're going to get something where this thing exactly divides this thing, and then the remainder will be 0. And once you get to that point where the remainder is 0, then you're done, and you just take sort of the last remainder you had. So the GCD of A and B is the last non-zero remainder. So that's the Euclidean algorithm. Just do these divisions, and then you take the last non-zero remainder, and that's the GCD. So it has nothing to do with prime factorizations. The fact that we could do division wasn't about prime factorizations. So like in that sense, we didn't need prime factorizations to do the GCD, and that's good because we want to sort of use actually the GCD to say something about prime factorizations. Okay, so let me do a more complicated example. So 756 times 360. So 756 is equal to 2 times 360. That gives me 720 plus 36. Okay, so actually this example didn't end up so complicated because now 360 is 10 times 36 plus 0. So 36 was the last non-zero remainder. So the GCD is equal to 36. Okay, so that was a lot easier than just computing the prime factorization to start out with. Like, unless you happen to notice that 36 divided 756, it would have been a lot more work to compute the prime factorization of this number than compared to the prime factorization here. Okay, good. And that's sort of the power of this, is that it gives you actually a pretty quick way so that's the computational power of this algorithm, is it gives you a pretty quick way to compute GCDs that, like, actually in practice is much more efficient than computing prime factorizations first and then comparing them. Okay, so here's another example I wrote down. This is sort of a worst case example, actually, in terms of efficiency. For computing a GCD of 144 and 89, I'm going to get 1 in the end because that's my last non-zero remainder. And it takes me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it takes me 10 divisions. But this is actually really as bad as it gets in the following sense. So you never need more than 5 times the number so you'll never need more divisions. You'll never need more steps. So each step is a division. Then 5 times the number of digits. In B. So here B was 89. So B had 2 digits. We needed 10 divisions, and that's actually like the most we could have needed. You can't write down an example of computing the GCD of 2 numbers where the second one sort of has 2 digits. Like, any such example will only take at most 10 steps. And of course, often it'll take much less than that. Like in this previous example, we had a sort of 3-digit number, but this only took 1 step or 2 steps. Okay, good. I want to point, and so this is something we're not going to talk about. This, like, how you show that this is how many steps it takes, is not something we're going to talk about in class, but there's a problem about this on the worksheet, and there's a discussion of this in the book. And this is actually sort of tightly tied to the following observation, which is if you look at this left-hand column, it might look sort of familiar because these are all Fibonacci numbers. So sort of the Fibonacci numbers start sort of 1, 1, 0. So 0, 1, 1, 2, 3, 5, 8, 13. So to get the next Fibonacci number, you sort of add the previous 2. So 2 plus 3 is 5, 5 plus 8 is 13, 13 plus 21 is 34, 34 plus 5 is 89, and so on. And actually, the fact that these are Fibonacci numbers plus a little bit of linear algebra is how you can actually justify the statement that you're never going to need more than 10 divisions. So if you're interested in, especially like if you're a computer scientist, you're interested in understanding efficiency of algorithms, this is a nice exercise to work through. So that's one of the last exercises on the problem sheet this week. Okay, good. But so just to recap, we want to prove uniqueness of factorization. Existence wasn't so bad. It just used the well-orderedness axiom. We had to make a digression in order to talk about uniqueness. So we'll finish talking about uniqueness next time, and uniqueness of prime factorizations and how you justify it. And the digression is we needed to talk about GCDs first. And really what we needed to talk about was this Euclidean algorithms, this specific method of computing GCDs. And so we're going to extract some statement, some slightly more powerful statement from this method for next time, and then we'll use that. But in the meantime, what I want you to take away is that we have this very efficient way to compute GCDs. And that's in practice quite useful. Okay, and so you'll get a lot of chance to apply that method this week on the problem sheet. Great, I'm going to stop there, and I will see you all in class.